Welcome to the 10th lecture of this course. I recall from the last lecture that given a subset S. So, for simplicity let us take S to be a non-empty one for any given non-empty subset. For empty subset we will see later, that is a trivial issue. So, for non-empty subset we recall that the set of all possible finite linear combinations from the set S, it forms a subspace of V. Not only that, given any subspace that contains that set S, this object, this subspace, if we denote it by star for the time being, the subspace denoted by star is also contained in W, right. All we have seen in the last lecture, and then equivalently we can also consider the following. We can consider the family of all subspaces of V which contains S. If we call this by, if we call this C, then this is also equivalent, we can see to be star in exactly in the same way, right, because this creature, this contains S. So, this star lies here, okay. So, therefore, intersection will be subspace of star, and now since star is contained in any such W here. So, the star will be contained in the intersection, hence they will be equal. Yeah. So, what I was talking about is this subspace denoted by star also admits two equivalent characterizations, namely this one, that for any subspace. So, this is its definition, this is an equivalent characterization and this is another. So, actually we have the description of this in three ways, okay. So, now we assign a notation for that. So, given any S, so given as S, this subspace is called the linear span of S. Linear span of S. So, there are several notations for that in the literature. One notation is LS, some authors write it by S like this, some paper in fact directly write span of S. So, we will mostly stick to this LS, okay. So, yeah. So, thus we have defined the linear span of a subset S of V. So, what is linear span? It has three equivalent descriptions. So, either in one description it is all finite linear combinations from elements from S. The another equivalent characterization a description is it is the smallest subspace containing S, and the thing, and the last one is the intersection of all subspaces containing S. Okay. So, thus we have defined linear span. Now, okay, so let us go ahead, that is better. So, regarding the, if you look for some, if you just to make sure that you have understood the concept of linear span, you can, so though the description is very much, I mean the description is very clear and explicit, still let us look at maybe some examples to examples of linear span of a set, just to make sure that you have understood. So, let us take anything, for simplicity let us take F to be R and maybe S to be the, let us start with the anything, say a singleton. So, the linear span is what we have defined RV is geometrically a line, okay. So, let us say yeah, so here V is R2. So, now let take V to be R3, take V to be R3, and then let S be the set of two vectors V and W. What is the linear span? So, let us try to see that geometrically. So, if this is our V and this is our W, then all the scalar multiples of V lies here, and the scalar multiples of W lies there, and when you add them you will get any vectors like this. So, therefore, what it shows is it is the plane passing through origin, right, containing the vectors V and W. Okay. Geometrically you can see it is a plane, but as we are habituated to see line and planes by equations. So, it is a quite natural question to for example, for line we have seen that we can in this case. So, this line we can view it algebraically by a linear by a usual equation. So, we should expect that here as well, that is given V and W, I should be able to write this plane, I should be able to express this plane as an equation. Of course, you can do that, but this is not quite easy as the case of a line. So, here you need to do something more. So, we will do that later. Okay. So, but the question is very pertaining that given V and W I should be able to. So, I mean by geometrically I can realize that there is a plane, but being rigorous or being more algebraic, if we want to make sure that indeed it satisfies the equation of a plane, then finding that equation is somewhat non-trivial, not as easy as the first case. So, we will do it, we need something more for that. I mean so right now it is not so obvious, but when we will go ahead we see that indeed we can do it. Okay. We need some more notions, namely orthogonality, then once in orthogonality, then that will tell me how to get the equation of this of the plane span by V and W. Anyway, so these are okay. So, here also I should note where here also I should make some note that what we said is not quite correct, because V and W that we have taken, they may be any vectors. So, always we won't get a plane. So, we will get plane unless and until V and W is one is multiple of the other. So, suppose if this is my V and let us say W is let us say minus half of V, then whatever combination that we take, we will always get the line joining V, W and U. Okay. Geometrically it will be a line. So, we will not always get planes, fine. So, let us please let us again focus on this case. So, what is the situation? Situation is, so let us call it S prime, where S is V W. So, we see that L S prime equals to L S, L S prime equal to L S, where S is a proper subset of S. So, given S, it might admit a proper subset S prime, which also gives rise to the same span. That may happen, and in this case that happens when we are dealing with two vectors, that happens if one vector is the scalar multiple of the other. Okay. We will come back to this phenomenon quite soon. Now, let us try to look for some more examples of linear spaces, linear span. So, I will just give only a few. So, suppose in this space of matrices, in this space of matrices, we let us for the sake of simplicity take 2 by 2. M2 and then R as well. If we just let us start with these two sets, the matrices of this type 1, 0, 0, 0 and 0, 1, 0, 0, and let us add one more 0, 1, 0, 0, then what is going to be its linear span? It's easy to see that alpha times this plus beta times this plus gamma times this, that means we will get the following matrix alpha, beta, gamma. Okay. So, for any alpha, beta, gamma you can take such a combination. So, that means the linear span of this is nothing but the set of all 2 by 2 upper triangular matrices. Okay. Then we also look for some other examples quickly. So, let us get into CXR, because they are in the list of in the examples of vector spaces. If you see, we put our emphasis on the function space, because this is a rich source of examples. Okay, this is a rich source of examples of vector spaces and then as well subspaces. So, yeah. So, CXF. So, what we do is, let us look at the linear span of the following subset. So, we do the following for each x. For each x in X, let us consider the following mapping. Ex is defined as, I want to define Ex as a map from X to F. How is that map defined? Ex of y is 1 if y is x, 0 otherwise. Okay. 0 otherwise. So, let me try to convince you the reason for let me try to give you some justification for writing the letter E here. So, if you remember that we were motivated to function spaces from one of the main points of motivation was Fn. So, what was Fn? So, we equivalently regarded Fn as the collection of all such maps. Okay. So, any tuple alpha 1 up to alpha n, starting with any tuple alpha 1 up to alpha n, we viewed it as the map which sends alpha I. Okay. Now, Fn, inside Fn we denote by EIs the vectors which has 1 at the ith coordinate and 0 elsewhere. Okay. So, this EI, when we want to review it as a map from 1 up to n to f, so what is going to be the map? This will be the map that sends I to 1 and else everything else to 0. Okay. So, for each point in this set we have a map that sends that point to 1 and everything else to 0. So, for each point I, the map we denoted by EI. So, we are kind of adopting the same notation or extending the same notation to the generality. Okay. So, for each x I have, so let us come back to the general situation. So, here S is the set. S is the set. The question is, what is its linear span? What is its linear span? So, as I said, by a linear span I have to, a typical member in the linear span of S will look like the following. For some alpha 1 up to alpha k and x 1 up to x k and k. Okay. So, remember this is a function. Okay. So, what is that? So, this is a function, right. So, what is the value of this function at a given point y? So, this function, so now this plus is in the sense of this plus is the addition in the vector space. So, this y, since the addition is defined as pointwise, so this will be alpha on ex on y plus alpha to x to y. So, this will be alpha I ex I y I from 1 up to k, and now use the definition of ex for general x. This turns out to be alpha I if y is any xi, okay, and 0 otherwise y is not equal to xi for all I. Okay. So, this happens to be the function which takes the value. So, we have a subset. So, on this subset it takes the values alpha i's. So, this function alpha 1 up to alpha k and 0, and it vanishes identically outside that set. Did we okay? So, that means the linear span is certainly contained. So, its linear span is certainly contained inside f of x, or in a different notation C0 xf. Okay, because any function vanishes identically outside this finite set. What about the converse? Suppose we are given a suppose we are given a function which vanishes outside a finite set, let us say x1 up to xn. I repeat, I want to show the converse. So, suppose let us take an f a function from here. So, how will a typical function look like? We simplify the notations, right. A typical function here will look like, as I said, I will express that by this notation. So, this formal symbol, this formal sum stands for the function that takes the values alpha I at the point xi and 0 elsewhere, I mean 0 at any other point, any points other than xi's. Okay. So, does this remind us, I mean does this somewhat shows us that this can be expressed as a finite linear combination from elements of S, right. So, what I mean is, suppose if I write alpha 1 E x 1 plus alpha k E x k, so is this equal to that? Exactly, because this function takes value alpha I at every xi and 0 elsewhere, the same, which is exactly same as this. So, actually this notation tells me that how to express that as a finite linear combination of elements from S. So, that is why I said that these notations will be more handy, more useful to us. So, the upshot is given this as the set, S is going to be the LS is going to be the full f x. That is, given S, this linear span of this S is the set of all functions which vanishes beyond a finite subset. Okay. And let us also see maybe one or two trivial examples, just to make sure you have understood what linear is. So, suppose x is itself finite, let us say x is 1 up to n. Okay. So, then what is and then we consider 1 up to n. So, then we consider E1 into En. What is the linear span of E1 into En? In general, it is going to be all the functions, so it vanishes beyond a finite set. When x is itself is finite, C0 fx is nothing but Cxf. So, therefore, this is nothing but the all function space which you equivalently regard as Fn. Okay. So, like I mean, instead of getting into the space of functions, you can do it directly as well, but we see that I mean most of our examples are somewhat coming from the function spaces. So, from that perspective, we deduce that f is generated by E1 E2 I mean Fn is the linear span of E1 E2 En, but as I said, you can do it directly because any tuple alpha 1 up to alpha n easily seen to be alpha I Ei. So, I mean when, as I said, when x is just a finite set, then tuple and the function we want to make any distinction. So, yeah. So, some examples of linear span we have given. Okay. Now, let us come back to the notion of, let us come back to the situation when a set, given a set x, given a subset x of a vector space V, it admits a proper subset, let us non-empty. So, assume this is non-empty, that is non-empty as well, admits a proper subset S such that they have the same phase. So, for example, our scenario is as follows, that is, suppose, I mean, let us simplify things for finite. I am just trying to talk about an instance. Suppose this is my S, then S has let us say, by deleting the last element, the span does not change. Okay. So, this is a situation for that. So, let us see if this happens, then what so the question is, since Vk, if you delete, well let me formally articulate that in the following way. So, let us stick to this situation. Suppose I have started with a finite set, and from that if we delete a single element, that is giving me a, so it is not changing the linear span at all. So, what is a typical element in the linear span? All possible combinations. So, if deletion of Vk does not affect the linear span, that means the combinations that you are for, I mean, if any combination with V1 V2 Vk is also a combination of V1 V2 Vk minus 1, then that means that Vk should be itself a combination of V1 V2 Vk minus 1, right, because Vk lies in this, Vk lies here, Vk lies in this space, therefore Vk will lie here, that means Vk will be a linear combination of the V1 V2 Vk minus 1. So, we see if this happens, then that means there exists alpha 1 up to alpha k minus 1 belongs to F such that Vk okay. In fact, it is if and only if. Why? If Vk is a combination of them, then any further linear combination of V1 V2 Vk there you can replace Vk by this, and then you can reduce this to a linear combination of V1 V2 Vk minus 1. Okay. So, that means that if by deleting one element from the set is giving you the same span, if that is there, then that element must be a linear combination of the others and vice versa. Okay. Now, we will well, so let us make a definition here. Let us make a definition here. So, given a non-empty subset, given a non-empty subset, S, and let us say V in V. So, let me put that in this way that okay, let's rather I'll rather come to it later. Let us first reformulate that in a different way, that will be helpful. So, suppose Vk is a linear combination of the other vectors, then you bring everything on one side, that gives you minus Vk is 0, right. So, if Vk is a linear combination of the other vectors, then you get a linear combination of V1, V2, Vk, where at least one coefficient is non-zero, namely here the coefficient of Vk, but the combination turns out to be 0, right. Okay. Now, what about the converse? Suppose you have the following, that you have a combination where one alpha I is non-zero. Well, let me very specific, where alpha k itself is non-zero. Then what happens? You can bring alpha k, this term to that side and divide everything by alpha k, then Vk becomes a linear combination of V1, V2, Vk minus 1. Okay. So, therefore, what we have seen is this happens equivalently, there is a combination such that the combination becomes 0, but the coefficient of Vk becomes, there is a coefficient of Vk becomes non-zero, the coefficient of Vk is non-zero. So, this happens if and only if, like we have try to place focus, we have three in a sense three equivalent characterizations which are very close to each other. One character, so linear span of these two is same as if and only Vk is the linear combination of others, if and only if there is a linear combination which such that the combination becomes 0, but the coefficient of Vk becomes non-zero. So, these three are equivalent. Okay. So, as we have seen that our intention is to, like you see that when we want to consider linear span, this Vk is not creating any, the Vk is not creating any, is not giving us anything extra while considering its linear combinations. So, we can simply, we can simply ignore that, right, because it is not giving us anything at the level of linear span. So, whatever you get from Vk, then that you can already get from Vk up to V1 up to Vk minus 1. So, if this happens, so it's therefore it's legitimate to call that, say Vk is dependent upon V1 V2 Vk minus 1, dependent in the sense that Vk can be achieved by them. So, therefore, from Vk, once you have Vk V1 up to Vk minus 1, then adding Vk with that you are not going to get anything else, taking linear combinations. So, we will make the formal definition here, that so let us go one by one. So, we say that V is linearly dependent on S if the what we have already seen, Ls is same as L of S union singleton V. Okay. And then we say that given a set, okay, let us say finite set for the time being, but we will see it does not matter. Given a finite set S, we say that S is dependent if there is x in S which is dependent on, which is linearly dependent on S minus x, right. This is the definition that you are going to say, or equivalently L of S becomes same as L of S minus x, right, or so yeah. So, this is equivalent to that, okay. We will say S is linearly dependent if there is a point in S, or another equivalent characterization to this definition is if S has a proper subset of a proper subset S prime has such that L of S prime becomes equals to L of S. Why these two are equivalent? Because first of all, if S is linearly dependent, then S minus x, if it is a proper subspace whose span is same as that of S, okay, and then the converse is very simple. If S prime and S, then S prime will mean some elements of S, okay. So we enlarge, for example, suppose S minus S prime, we have started with a finite set. So S minus S prime, let us say it will have some elements U1, E2, UR. So you just add U2 up to UR to S and make it S double prime, okay. So therefore S double prime, leave S double prime, only S double prime has all the elements of S except U1. Now it is easy to see that L S prime is a subspace of L S double prime, okay, and both are subspaces of L S, okay. But since I know this equals to that, so therefore in the midway everywhere there will be equality. So thus we have a situation like this, that by missing one point the linear span is same, okay. So this is also an equivalent way of putting the linearly dependence. Well, so here you might raise one objection that while defining linear span I consistently take that to be non-empty set. So what happens if we just consider empty set? So for that we define linear span of the empty set is the trivial one. Linear span of empty set is the trivial one. You might raise an objection that how I can say that, because I am not allowed to consider any combination because phi contains nothing, but the justification for which considering this as this is the third description, that is the linear, I want the linear span to be the intersection of all subspaces, okay. So the smallest one, so this happens to be the smallest one. So that in view of that, it shows that if x is just some singleton, then this is not linearly, so and A is non-zero. So then such an S cannot be linearly dependent, okay. this cannot be linearly dependent, because its span is non-trivial, where when you miss that point the span will be trivial. Okay. So, we have well, so here also let me remind you that is all very easy to see. So, for is a basic property of linear span, that if S is a subspace of T, then LS is a subspace of LT, that we have actually used here, which is very easy to see, because every linear combination from S automatically becomes a linear combination in T. Okay. So, so a set is linearly dependent. For finite set, it is linearly dependent if it has a point such that if you miss that point, there will be no change. If you delete the point from that set, delete that vector from the set, the linear span will remain the same. Okay. Or another word is there is a finite subset of that finite. So, since you are starting with a finite set, so a finite subset of that means possibly deleting several points. So, there also we are not getting any change at the level of linear span. Now, I will make another equivalent definition of the linear dependence. If you remember that V k is linearly dependent on V 1 to V k minus 1, equivalently we have a combination having, we have a linear combination having the coefficient of V k non-zero, but the combination happens to be 0. So, equivalently there is a, so let me better way of writing that is the following, that we label the elements of V as V 1 V 2 V k. So, if the equivalently there is, so setting V s equal to V 1 V 2 V k, there exist scalars alpha naught to alpha k such that at least one alpha is non-zero and summation alpha I V I is 0. Okay. Why is this equivalent? Because if you just compare with that, so it's linearly dependent means there will be a sum V I, if you such that if you delete that V I, then the linear span of the rest is same as the linear span of this, and that is same as you will get a combination which becomes which is the, you have a combination which is 0, but the coefficient of V I will be non-zero. So, that is what is there. So, thus we have defined linear dependence of a set of vectors in 3 equivalent ways, namely the first one says that if there is a vector in that set which is linearly dependent upon the rest, the second one says that it admits a further proper subset which also gives rise to the same span. The third one is purely in terms of linear combinations. So, while checking a given subset is linearly dependent or not, this one seems to be, this one, I mean we will see that this one becomes more easy, I mean not easy, this one becomes more useful, because otherwise every time what you have to do is, if you start with this, you have to pick up every element and then see whether it can be expressed or not by so rather than that, it is rather easier to show, rather than that it is easier to find out a combination which often becomes easier from some other way. It is a combination such that where at least one coefficient is non-zero. Okay. So, this is what we know when we say a set is linearly dependent. Okay. Let us look at an example. Already we have talked about an example that if S is a singleton set having a non-empty with a non-zero vector, then S cannot be linearly dependent. Now, if you look at another example So, let us come back to the example of the example that we have been motivated with, that is in R 3. We take two vectors v and w. So, we have observed that its linear span is the, we have realized that geometrically it is a plane, if one is not the scalar multiple of other, otherwise it is a line. Okay. So, this set is linearly dependent this set is linearly dependent. So, if so the definition says either v equal to alpha w for some w for some alpha or w equal to some beta v alpha dash v for some, this is just the definition that one will lie in the linear span of the other, and equivalently the important part is equivalently, this is a geometric description that the is geometrically a line. So, that as I said that is a geometrically this is not a rigorous proof, because lines we have not defined rigorously what we mean by a line. So, in 3 dimension. So, and if you want to, and then passing through the, I mean if you want to see that by writing equations, that is not easy, that does not seem to be easy till now, because well, let us not get into that. So, this is geometrically, I mean the geometrically when we realize a given subset of R 3 is linear dependent. So, geometrically it is a line passing through origin. Okay. Let me repeat, I constantly say that this is geometrically, because we have not proved, we have not formulated, like by drawing the picture what we see, that cannot be regarded as a rigorous proof, right. So, the rigorous proof is to be done by means of considering equations, but as I said that it is not so trivial from it does not seem to be so trivial from what we have discussed right now, but later on we will go ahead, we will see that indeed by considering considering the equations of lines and planes, we can we will be able to show that as I said, when I characterize lines by equations algebraically that you do in analytic geometry, then we will be able to justify this fact rigorously. Okay. That is the matter of later. Let us now come back to linear dependence. So, yeah, for a set of two vectors, we have seen, and even if instead of R 3, if you take any other vector space and set of two vectors v and w, then this linearly dependent if as by if, but if I mean if if the set is linearly dependent, if one is the scalar multiple of other, that is just by definition. And yeah, now let us go ahead. If a subset is not linearly dependent, then we will call it linearly independent. Is said to be linearly independent independent. I repeat, the sense of this word linear dependence is in the sense that it has an element which is expressible as a linear combination by the other elements, that is, that element is linearly dependent. The reason for call it linearly, because here we have all the combinations we are calling as linear combinations. So, there is a linear combination, therefore, if x is a linear combination of some element, then you will say that x is linearly dependent on upon the other elements. So, linearly independent means there is no x in that set which is linearly dependent on others, or in other words, linearly independent if it is not, So, linearly independent means there is no x which is linearly dependent upon other elements. So, or in other words, if the set there is no such Sx means is not linearly dependent. If it is not linearly dependent, and then we must have equivalent characterizations here. So, so again here it means not independent, that for every x in S, L of S minus x is will be a proper subset of L of S. Okay. This is just the negation of this. Equivalently, it will be the negation of that there exists for every just a minute. And then finally, this one, that well let us do that for assuming finite. So, if S is, if we label the elements V1 V2 Vk, if S is V1 V2 Vk, if we have a combination where with alpha is belongs to F, then we must have, then one has all alpha i's to 0. So, just so linearly independence means the opposite linear dependence. So, therefore, this is equivalent to the negation of that and then following the negation of that. So, this is the definition of linear independence. So, with that I will finish this lecture. Next lecture I will focus more on this linear dependence and basically more on linear independence. So, okay. So, thank you.